Okay, we begin the 5.4 concavity in the second derivative test page. You can go ahead and read this. As you see, there's a yawn in there, so it's a little bit boring. So we're going to be talking about something that is actually pretty exciting. So if you take a look at these two functions, one of them, they're both increasing, but they're increasing differently. So they have different concavity, and that's our big word of the day. So this increases at an increasing rate, the first picture, and the second picture increases at a decreasing rate. So we're talking about how things are changing, and that's what calculus is all about. So, for example, these slopes here, the slopes are increasing. And you could probably take a guess at where this is going because slope is just another word for derivative, and we're going to be analyzing derivatives. In this one, however, the slopes are decreasing. Okay, and we'll be talking a lot more specifically about this very soon. Alright, so we're talking about the second derivative when we say the slopes are increasing. We're talking about how the slopes are changing. So if the tangent lines are below the curve, such as something like this, the tangent lines would be below the curve, then we're going to call this concave up. I could explain this in a lot of words, or I could draw a nice picture. So we got a happy guy and an unhappy guy. So this is going to be concave up. His smile is concave up, like a cup. And this unhappy guy, his smile is concave down, like a frown. If you say that enough times, it's going to stick in your head, and it's going to help you analyze these graphs. So concave up like a cup and concave down like a frown. So we're going to list in example 3 the open intervals on which the graph of the function is concave up. So we want concave up like a cup, concave down like a frown. So we have concave up. It's going to look like a smiley face. So it looks like from here to here, here to here, and here to here. Concave up like a cup would be from B to C, from D to E, and also from E to P. And notice I put two different intervals for D to E and E to P. On the other hand, we have these ones. So it's concave down from A to B, from C to D, and also from P to Q. So the concavity changes at each of these values. And those will be important very soon. All right, so when we're trying to find what values the function can change its concavity, these are called points of possible inflection values, or PIVs. So to test the intervals for concavity, we're going to find any discontinuities. We're going to identify possible inflection values by finding where the second derivative is 0 or the second derivative is undefined. We're going to use a number line chart and test the intervals for the sign, whether it's positive or negative. When the second derivative is positive, it's concave up, like a cup. And when the second derivative is negative, it's concave down, like a frown. Okay, so here we go. It has an inflection point when it changes from concave up to concave down, or from concave down to concave up. This is very similar to our first derivative test. Right, concavity can also change at a discontinuity, but it won't be an inflection point. Okay, so if we had something like this and this, it's going to change at that vertical asymptote, but it's not an inflection value. And not every possible inflection value is an inflection value. And a chart will help us organize our thoughts with that. All right, so for example 4, we're going to determine the open intervals where they're concave up or concave down. So this implies we're going to have to find the second derivative. So we have y prime equals cosine of x, and y double prime equals negative sine of x. We need to figure out where that's 0 or undefined, and we know that sine of x equals 0 when x is pi, 0 pi or 2 pi. So I'm going to place those numbers on my number line. So those are my x values, and I'm going to be plugging them into the second derivative. Now I'm only concerned about this interval, so I'm not going to pick numbers smaller than 0 or greater than 2 pi. So if I pick something between 0 and pi, I'll have pi over 2. If I pick something between the other ones, I'll have 3 pi over 2. So the sign, negative sign of pi over 2 is going to give us a negative, because sine's positive 1, so negative 1, there we go. And remember, we're plugging this into the second derivative. So now this sign will be positive. So we're listing that the function y is concave up like a cup on the interval where the second derivative is positive. Y is concave down like a frown where the second derivative is negative. Okay, and then find any inflection points. Y has an inflection point at x equals pi. Since, and you do have to justify this, y double prime changes from negative to positive at x equals pi. And that little bit right there is enough to justify the problem. So let's move on to 4b. You could write this as 6 over x squared plus 3. But I don't feel like using the quotient rule, so I'm going to go ahead and just use the power rule for this one. So we have f prime of x equals negative 6 times x squared plus 3 to the negative 2 times the derivative of the inside, which is 2x. So another way of writing that would be negative 12x times x squared plus 3 to the negative 2. And again, here you can write it in the quotient form and use the product or the quotient rule, or you can just use the product rule, leaving it in this form. So if I go ahead and find my second derivative, I have the first times the derivative of the second plus the second times the derivative of the first. Now let's clean this up a little. So we have negative, what's that, 48x squared times the quantity x squared plus 3 to the negative third minus 12 times the quantity x squared plus 3 to the negative 2. Here's a time for one of our favorite things, factoring out least powers. All right, so I'm going to take out a negative 12 as my constant. Both of the terms don't have an x, so we can't do that. So I'm going to go ahead and take out x squared plus 3 to the negative third. Okay, let's see what's left over. We would have 4x squared, and we factored out the whole x squared plus 3 term. And on the second one, we're going to have plus negative 3 plus what gives you negative 2, and that's going to be 1. So I have x squared plus 3 to the first power, making that big beefy bracket area look a little bit better. I have 4x squared plus x squared gives me 5x squared. Okay, plus 3. And I'm going to go ahead and move that second part to the bottom. Now I just saw one mistake that I made that's going to make a huge difference. This should have been a positive 48, which means that would be a negative 4x squared, which really turns this into negative 3x squared. Woo, good thing I caught that. Alright, so now we got to find our possible inflection values. And remember, that's where our second derivative is 0 or undefined. If we analyze the denominator, that's never going to be 0. So we're not going to have any undefined values. When this factor equals 0, then our second derivative equals 0, and we'll have our possible inflection value. So x ends up being positive or negative 1. So let's put those on our number line. Those are our x values. We're evaluating the second derivative. Pick some numbers in between that are part of the original function. Okay, which is all real numbers. So we have 0, 2, and negative 2. You can plug in whatever you want. You should get positive, negative, positive. So our function f, let's see, I want to go back to green here. F is concave up like a cup from negative infinity all the way up to negative 1, and also again from 1 to infinity. F is concave down like a frown in between those, negative 1 to 1. We have F has an inflection point at x equals negative 1 and x equals 1. I'm going to break that down, actually. It's better to describe each one individually. At x equals negative 1, since f double prime changes from positive to negative, and x equals 1, since f double prime changes from negative to positive at x equals 1. So there you have it. I would like you guys to try 4C and determine the intervals of concave up, concave down, and whether it has any inflection points, and if so, what are they? So thanks.